right, for the second of this week's virtual asynchronous lectures that I'm putting together, we're going to cover the third major reaction type for aqueous solutions, which is redox reactions. Before I get into it, because I won't see you guys until after spring break, I wanted to give you the first notice about the midterm 2 review. Feels like we just had a midterm, but we have to start thinking about the second one already. So again, it's still a while away, but with spring break in the middle, I want to make sure you're aware that it's coming up sooner if we get back. So let me make sure all right, make sure I get the date right. It's going to be March 24th, Friday. It's going to be 2 p.m. and the room number is a little bit different than where we have class. It's going to be SEC 103, which is 2 doors down from where we have class. So it's that location in person. I will record it just like I always do for everything pretty much, but it'll be in person this time and not on Teams. All right, but that's still over 2 weeks away from this lecture, but with spring break in the middle, it's going to come up fast. Okay, so last time in the lecture we just had on Tuesday, also recorded, we covered the first 2 major types of aqueous chemical reactions, and the first of those 2 was precipitation reactions, where you have 2 ionic compounds reacting, and they form 2 ionic compounds as a product, and if there's one of those that's insoluble, it will form a precipitate, and that would be then the net precipitation reaction. So write the balance equation for the reaction of sodium phosphate and calcium chloride in aqueous solution, and then determine what substance will precipitate. All right, so for this one here, what we're going to do is we're going to write out the 2 reactants first. And so what we'll have then in this case is, sorry, give me a second, I'm a little bit disorganized here. All right, so we have sodium phosphate and calcium chloride. So those are going to be the 2 aqueous solutions we're combining. So sodium phosphate, sodium is Na+, first column periodic table there. Oh, I'm zooming in too far. Get a little bit. All right. So anyway, sodium is here in the first column, Na+, and it's going to combine with phosphate, which is PO4 3-. So the correct formula for sodium phosphate is Na3PO4. So we do have to be good at getting formulas for ionic compounds in this section. So that's going to be our first reactant. And then our second one is calcium chloride. So calcium is Ca, which is second column now. So it's going to be calcium 2+, with chloride, which is Cl-. So CaCl2 is the second reactant. And then those are going to combine, and they're going to form 2 product where we're just going to swap cations and anions. So the cation from the first is sodium, that'll combine with chloride to make sodium chloride. And then the cation over here is calcium, which is Ca2+. This formula is going to be a little bit weird, but calcium 2+ is the second one, PO4 3- is the anion, and so when we make that compound and balance the charges, what you're going to get is Ca3PO4 2. Okay, so those are the reactants and products. Now we have to decide which, if any, of the products is insoluble. So all sodium salts are soluble. Sodium chloride is just salt, as we know, that dissolves in water. So that's going to be AQ, aqueous. But then calcium phosphate, almost all phosphate salts are insoluble unless it's lithium, sodium, potassium, one of those special group 1A cations. So this one's going to be our precipitate there. All right, so that's going to be the balance equation, and then this one here is the precipitate, the one that's insoluble. All right, so that's an example of a precipitation reaction that we covered last time. And then the other major category we did was acid-base reactions, where you have acid plus base gives you water plus ionic compound. So here we have sulfuric acid and lithium hydroxide. We can recognize this as acid-base. First of all, the word acid is directly in the name of that, and then hydroxide, OH- is what signifies something as a base. So for that reaction, how many moles of water are formed when the reaction is balanced with the smallest whole number coefficients? So when we balance this one out, we have sulfuric acid as the acid, which comes from SO4 2-. So the acid of that is going to have 2 hydrogens in the formula to balance the -2 charge. So the formula for the acid is H2SO4, and then lithium hydroxide. Lithium is Li, first column of the periodic table, and so it's going to be lithium +1, OH -1, so you're going to have LiOH is the equation for that. And then the products for an acid-base reaction, we always have water as one of the products, and then an ionic compound, which in this case is going to be lithium paired with sulfate. So the formula for that would be Li2SO4, and that one's going to be soluble because all lithium salts are soluble. All right, so those are reactions and products. Now we have to balance this one to answer the question that's being asked, which is how many moles of water are formed, or what's the coefficient for water. So when we look at this one here, we have 2 H pluses from our acid, so we need 2 OH minuses to react with that. This only has 1 OH minus in the formula, so it's going to require a coefficient of 2. And because we have 2 H pluses and 2 OH minuses, that's going to form 2 moles of water. All right, so 2 would be the correct answer here, is how many moles of water form. No coefficient is needed in front of lithium sulfate. That one's already balanced. All right, but when you have a diprotic acid, an acid with 2 protons like H2SO4, 2 H pluses, 2 OH minuses will combine to form 2 waters. So that's a bit of a review of what we did last time, just a couple of examples. But what we're going to talk about today is another category of aqueous chemical reactions called redox reactions. Now, the reason they're called redox is because they combine reduction and oxidation. So oxidation is when something loses electrons. Reduction is when something gains electrons. And when those two things happen together in a chemical reaction, they always come together. You can't create or destroy electrons. So if something is losing electrons, something else is gaining electrons and vice versa. So these always happen together, and so we call it a redox reaction. Something is being oxidized and something is being reduced together, and we call it a redox reaction. So more generally speaking, it's a reaction that involves electron transfer. One or more electrons is being transferred from one reactant to the other to form the products. All right. So the 2 previous reaction categories we talked about, acid base and precipitation, are not redox reactions. This one is distinct from those 2. This is the only type that involves a transfer of electrons. Now, to remember the terminology, how do I remember that oxidation means losing electrons, reduction means gaining electrons? There's a simple mnemonic device here. So Leo is sort of the Latin root for lion. So if you have a lion named Leo, what does a lion say? We learned this back in probably preschool. Lion says grr. All right, so this is how you remember it. Lose electrons is oxidation. Gain electrons is reduction. Leo says grr. So that's how I remember the difference between reduction and oxidation. So when something loses electrons and then gains electrons, that's oxidation and reduction. Now, how do we decide, though, in a chemical reaction, whether something actually loses or gains electrons? I mean, sometimes it's obvious. Sometimes the charge of the whole thing changes. So if you have sodium metal, which is zero charge going to sodium plus, which is +1, obviously they had to lose an electron for that to happen. So that makes it pretty obvious. But in other cases, you just look at the formula of the reactants and the products, you can't clearly tell whether reduction or oxidation is happening. So the way that we can figure that out is by looking at the rules for oxidation numbers. And so oxidation number is basically something that we assign to every atom in a compound, and it allows us to then decide, based on that oxidation number, if that oxidation number is changing between reactants and product side, that means that that element, or that atom, is losing or gaining electrons. So we use oxidation numbers to help us easily determine and easily sort of confirm whether reduction or oxidation is happening. So oxidation rule oxidation numbers are kind of like formal charges, but they're defined a little bit differently, and you can't use formal charge for this purpose. You have to use oxidation number. So an oxidation number is basically an ionic formalism. So if you remember formal charge that we did in chapter 3, a formal charge assumes that the bonds are perfectly covalent, and then ask, okay, what would be the charge on this atom if we split up the electrons equally between the two, the bonded electrons. An oxidation number is an ionic formalism which assumes that the more electronegative atom gets all the electrons in that bond. And then we basically, every covalent bond in the molecule, we sort of break it up such that all the electrons go to the more electronegative atoms, and then we look at what the charges of those atoms would be if we distributed the electrons in this way. So it's totally a formalism. It has no real physical meaning. It's not something that tells us much. It's just an accounting tool for us to figure out whether or not something is gaining or losing electrons. But first we have to learn how to do it before we can see how it applies to redox reactions. All right, so the first rule, which is probably the most important, is that the sum of the oxidation numbers equals the total charge of the ion or the compound if it's a neutral compound. So if you have a neutral compound, the sum of the oxidation numbers for that whole compound equals 0. If it's an ion, the sum of the oxidation numbers equals the charge of the ion. So that's kind of similar to formal charge. We saw the same thing for formal charge. The sum of the formal charges equals the overall charge. But again, they're assigned and calculated in different ways. So there's some that are easy to remember, and we'll start with some of those. So the first is that if you have an atom in a neutral element, so, Na by itself, or N2 is part of dinitrogen. But if it's a neutral element, no charge, and just one type of element in the formula, the oxidation number for all those is 0. And that's the only time the oxidation number is 0 for our purposes. So elements have 0 oxidation number. But then for everything else that's not an element, either an ion or a compound, then you're going to have non-zero oxidation numbers. So let's learn how to assign some of those. So the first is that if you have a monoatomic ion, so that would be something like Na+, K+, Fe2+, whatever it is, and a metal with a plus charge, or anything with a plus charge, is by itself, the oxidation number is equal to the charge. Now, it's also true if it's part of an ionic compound. So if you have an ionic compound, we know how to assign the charges of the ions. And if it's a monoatomic ion, just, a cation if it's a metal, or an anion if it's a non-metal, like Cl- or O2-, the oxidation number is equal to the charge of that ion. So for ionic compounds, it's usually pretty simple to get oxidation numbers, especially when polyatomic ions are not involved. And so, kind of similar to that, then this is sort of just an extension of that. If you have a metal that's part of an ionic compound, we can use the formula of that compound and the anions that it's paired with to be able to assign the charge, and the metal in that compound is going to have an oxidation number equal to charge. So it looks like my tablet died, so I'm going to have to pause this and come back with the rest of this, so I apologize for that. All right, I apologize for the discontinuity. My tablet stylus stopped working again, which will never stop annoying me, but we're back, and I'm going to continue off with where I left, where I left off. All right, so we're talking about oxidation number rules, and if you have a metal in an ionic compound, so if you have either the ion by itself, the oxidation number is equal to the charge, or if the metal's in an ionic compound, then you're going to have, that got all messed up, so I'm having all kinds of struggles today, but we're getting there. All right. Let's go back and finish these rules. All right, here we go. So metal in an ionic compound is going to always have a positive oxidation number, and it's going to be equal to whatever its charge is in that compound. All right, so that's another rule. Now for the nonmetals, particularly when they're in covalent compounds or polyatomic ions, things are a little bit more complicated, but there's a few easy ones to look for. So hydrogen is one of them. Hydrogen would be 0 if it was just the element hydrogen, H2, but it only has two other possibilities if it's in a compound. It's going to be +1 when it's bonded to a nonmetal, and we haven't really talked about compounds of this type just yet, but if you have hydrogen bonded to a metal or a metalloid, it's going to be -1. So if it's bonded to a metal, it's called a metal hydride compound. It's a kind of sort of ionic compound, but not one we've talked about a lot or will talk about a lot. But when it's bonded to a metal, hydrogen has a -1 oxidation state, or also to metalloids. Classic examples being boron and silicon. So when hydrogen is bonded to those, is -1. But in most cases, for the types of things we'll work with, hydrogen is +1. For fluorine, it's always going to be -1 anytime you have a compound with fluorine in it. So whether there's an ionic compound, covalent compound, fluorine is always -1. And that's because when we're doing oxidation numbers, we're giving the electrons to the more electronegative atom. Fluorine is the most electronegative atom, and so it's going to always be -1 when we divide the electrons up that way. So fluorine is always -1. That's an easy one to look for. And then oxygen is another fairly easy one to deal with. Oxygen is usually -2 whenever it's in a compound. Again, it'll be 0 if it's the element, but if it's in a compound, it's -2, except when it's bonded to itself or fluorine. So there are rare examples of compounds where oxygen will be, -1 or even +1, depending on what it's bonded to. If it's bonded to anything but itself or fluorine, it'll be -2, and that's usually the case. And then finally, the last rule that's worth covering is that if we have other halogens besides fluorine, these are usually going to also be -1, unless they're the central atom in the compound. So we have some compounds that have, or especially polyatomic ions that have halogen central atoms. So that in that case, their oxidation number can be something different, or if they're bonded to oxygen or fluorine. And usually when they are the central atom, they're bonded to oxygen or fluorine anyway, so this rule kind of is two ways of saying the same thing. So those are rules for oxidation numbers. Some of them will come up more than others, but we just have to get familiar with them and learn how to assign oxidation numbers, because that's going to be a part of what we do in terms of both deciding whether or not something is a redox reaction, and then once we go to balance them later on, these oxidation numbers are critically important. Let's do a couple of examples where we're just going to assign the oxidation numbers in different types of compounds. So if we have sodium sulfide, that's what it looks like over here on the right. What is the oxidation number for each element? Well, we should recognize, based on the locations on the periodic table, that sodium Na+, and then sulfur S2-, that's going to form an ionic compound, metal with a nonmetal. So we use the charges of those to predict the formula. So sodium is Na+, sulfur S2-, and so the correct formula of this compound would be Na2S. So that's the formula of the compound. But then for the oxidation numbers, remember that in an ionic compound, particularly one that's just a binary ionic compound like this, the oxidation numbers are just equal to their charge. So the sodium ions are +1, so they're going to have a +1 oxidation number. And then the sulfide ions are -2, so sulfur is going to have a -2 oxidation number. So for ionic compounds, it's as simple as that, particularly when they're binary ionic compounds and it's just everything's monoatomic anion. And so we said the sum of the oxidation numbers should equal the overall charge. This is a neutral ionic compound. So if we look at the sum, we have 2 sodiums in the formula. Each of them is +1. And then we have 1 sulfur in the formula that has an oxidation number of -2, and those add up to 0 as they should. So it's important to recognize and realize when you're assigning oxidation numbers, they apply to every atom in the formula. So when we say that sodium has a +1 oxidation number, it's not that +1 is the combined oxidation number for both sodiums. Each individual sodium atom, or sodium ion in this case, would have a +1 oxidation number. So 2 sodium ions, each with a +1 oxidation number, 1 sulfide with a -2 oxidation number. So for things like that, it's pretty straightforward. But if we go on to some covalent compounds, then things get a little bit more challenging. We have to use a little bit of algebra to help us. So determine the oxidation number of each element in phosphoric acid. So we have to get the formula of the compound correct first. Phosphoric acid comes from the phosphate anion, which is PO4 3-. So the formula would then be H3PO4. All right. So for assigning oxidation numbers, we want to look for the obvious ones first. So if we have a covalent compound, so the three elements are hydrogen, oxygen, and phosphorus. In a covalent compound, any acid or any covalent compound that involves hydrogen, the oxidation number for hydrogen is going to be +1. For oxygen in the vast majority of compounds that it forms, it's going to be -2, unless it's bonded to itself. In these oxoanions, remember that the oxygens all surround the central atom like this. There's formal charges on each of those, some lone pairs I'm not drawing. But in these oxoanions, or the acids that form from them, oxygen is not bonded to itself. It's bonded to the central atom only. So again, rare exceptions of oxygen not being -2. So those two are easy to assign. But then to get phosphorus, the central atom usually is going to have a variable oxidation number, and we have to use a little bit of algebra to figure out what phosphorus should be. So this whole compound H3PO4 is charge neutral, so the sum of the oxidation numbers has to equal 0. And that has 3 hydrogens in the formula, which we determined are each +1 oxidation numbers. 4 oxygens in the formula, which are each -2, and then whatever the oxidation number is on phosphorus. So we're usually going to do that by difference at the end. There's no set rule for phosphorus. Most of the elements in group 5, I guess, where phosphorus is, nitrogen, phosphorus, and so on, they have variable oxidation numbers. So we're going to do those last. But the sum of all of them has to equal 0. So this is the oxidation numbers for the 3 hydrogens, for the 4 oxygens. So those add up to -5, so you need a +5 on phosphorus to balance it out and have them equal 0. So phosphorus should get a +5 oxidation number to ensure that all of the oxidation numbers add up to 0. So when you have covalent compounds, look for hydrogen and oxygen first, because with a rare exception, they're going to be +1 for hydrogen, -2 for oxygen, and the rest you go from there. So a very similar one now is if we just look at an anion by itself, sulfate. So this time we don't have the acid, we just have the anion, SO4 2-. Oh, come on. All right. Sorry, my tablet's not liking that I'm trying to do 3 lectures in one day, apparently. All right, so we have SO4 2-, and when to determine the oxidation number for each element here. And so again, what we have is oxygen in a covalent compound. The structure is shown here. Again, all these oxoanions, there's no oxygen-oxygen bonds. They're all just bonded to the central atom. So we're still going to have -2 for oxygen whenever it's in a compound. And then we have to figure out what sulfur is by difference. So the only difference here is that in this case, because it's a -2 anion, the sum of the oxidation numbers won't equal 0. They'll equal -2, which is the overall charge. So when we set up the little bit of algebra that we have to do to find sulfur's oxidation number, this time -2 is the total charge, and that's going to equal the sum of the 4 oxygens, which is -2 each, plus the sulfur in the middle. And by algebra, we know that that has to be +6 for this to add up to -2. So 4 -2s and a +6 gives us a -2. So sulfur would be +6 in this compound. One thing that's a little bit helpful for oxidation numbers is to check yourself. I guess you could put it down as a separate rule, but it's just a good check more than anything. The group number for the main group elements, we're going to primarily be dealing with main group elements, group 1A, group 2A, 3, 4, 5, 6, 7, 8 over here in the P block. The highest oxidation number that they can possibly have is equal to the group number. So sulfur's in group 6, +6 is the highest oxidation number it can have. It doesn't have to be +6, but it won't be anything bigger than that. You'll never have +7 or +8 on sulfur. So the group numbers give you the highest oxidation number, but again, for some of these group 5, group 6, group 4, especially these sort of middle P block elements here, they do tend to have variable oxidation numbers, so they can be a lot of things, but never bigger than their group number. All right, so that's how we assign oxidation numbers. Now, how is this important in a redox reaction? So when you have a redox reaction, as we said, you have a transfer of electrons, you have one reactant getting oxidized, one reactant getting reduced, and what we call those are the oxidizing agent and the reducing agent. Now this terminology is a little bit confusing because the oxidizing agent is going to be the reactant that gets reduced. Now you might think we're trying to deliberately confuse you by saying that the oxidizing agent is the one that gets reduced. Why are you doing this to us? Well, if you think about what agent means someone that does something. So the oxidizing agent is the reactant that does the oxidizing. It causes something else to get oxidized. Remember, these always go together. So it's a little bit confusing, but you just have to remember that the reducing agent is the one that does the oxidizing, which means that it gets reduced. The oxidizing agent does the oxidizing, gets reduced. Now, how do we identify that in a chemical reaction? Well, this is where oxidation numbers are going to help us. If you have something on the reactant side and the product side, you compare the oxidation numbers. If the oxidation number reduces or decreases during the reaction, that's going to identify it as the oxidizing agent. So that will be the one that gets reduced, the one where the oxidation number gets smaller during the reaction. All right. Now the other one that we have is the opposite, is reducing agents. This is going to be the reactant that gets oxidized in a chemical in a redox reaction. And again, we call it a reducing agent because it's the one that does the reducing. It causes something else to get reduced, so it's the reducing agent. And opposite story is true, as oxidation number is going to increase during the chemical reaction. All right, so those are the terminology we use to identify the oxidizing and reducing agent. And again, this is how we sort of decide if something is an oxidation reduction reaction, a redox reaction, whether there are changing oxidation numbers. Now, as a little bit of an aside about this terminology, usually in an oxidizing and reducing agent, just one atom in that whole formula is going to change its oxidation number if it's a complicated molecular formula. But we still call that whole molecule, that whole thing, as the oxidizing and reducing agent, even though only one of the atoms is changing its oxidation number. So we'll see that a little bit later on. But let's see how we do this and how we use oxidation numbers in identifying redox reactions and identifying oxidizing and reducing agents. So we have this reaction here, PCl3 phosphorus trichloride plus oxygen goes to 2POCl3, phosphorus oxychloride is what it's called. So to decide if something is a redox reaction, we have to assign the oxidation numbers for every atom on the reactants and product side and see if we have any that are changing. If there's no changing oxidation numbers, then it's not a redox reaction. So let's do that for this one. So for PCl3, chlorine is going to be -1 when it's not the central atom. So if we have 3 -1s from chlorine, that means that phosphorus has to be +3. We don't need to worry about coefficients when we're assigning oxidation numbers, just the formula of the compound. So PCl3 has 3 -1 for chlorine and a +3 for phosphorus. O2, it's an element, a neutral element, no other, it's not bonded to anything else, no charge, so the oxidation number will be 0 anytime it's in its elemental form. And then for POCl3, what we have is, again, chlorine is the non-central atom, is going to be -1. Oxygen in covalent compounds is -2. So we have 3 -1s, a -2 from oxygen, that's -5, which means that phosphorus needs to be +5 for all of those to add up to be 0. All right, so definitely make sure you're familiar with assigning oxidation numbers. We just covered it a little bit ago, and you need to be proficient at it for these types of problems. So those are all the oxidation numbers on reactants and product side, and what we see, if we're evaluating question A, is this a redox reaction? Well, what we see is that phosphorus is changing from +3 to +5. On the reactant side, phosphorus is +3, on the product side is +5, so that's a changing oxidation number. And there will always be a pair that are changing. So for oxygen here, it starts out as 0 as the oxidation number, and it goes to -2 on the product side. So because we have changing oxidation numbers, phosphorus going to from +3 to +5, oxygen 0 to -2, this has to be a redox reaction. So the first answer would be yes, it is a redox reaction. And so because it's a redox reaction, we can identify then the oxidizing and the reducing agent. So we're looking for the oxidizing agent here. The oxidizing agent is the one that gets reduced. Again, the terminology is a little bit weird, but you have to get used to it. The oxidizing agent gets reduced, which means that its oxidation number decreases during the reaction. As we said, in oxygen, the oxidation number starts at 0. On the product side, it changes to -2. So this is the one where the oxidation number is getting smaller. O2 goes from 0 to -2. So then we identify O2, that whole thing, not just oxygen atoms, but O2 itself, as the oxidizing agent. Now, one shortcut that's helpful for identifying redox reactions is that if one of the reactants or products, at least one of them, is an element, so here we have O2, which is the elemental form of oxygen. If you have an element on the reactants or product side, it has to be a redox reaction. Now, why is that? Well, because elements, those are the only times when you have 0 oxidation number. So that means if it's 0 on one side of the equation, it has to be something else on the other side of the equation, because it can't be an element anymore if it's reacting to form something new. So whenever you have elements involved, it's going to be a redox reaction. That's a nice, easy way to identify them. But they don't all have elements. There are redox reactions that don't involve elements, of course. But if you have a neutral element, plain old element by itself, as one of your reactants or products, that must be a redox reaction. This is an example of that here. Now let's go to the next one, which looks similar reactants and products, also a phosphorus reaction, but we're going to see if this one is a redox reaction. All right, so we have to assign oxidation numbers again for this. So POCl3, that was the product of the previous one, and we saw that phosphorus was +5, oxygen -2, chlorine -1. So again, we assigned those in the last one, so you can go back to see how I did that. But Cl is -1 in compounds, oxygen is -2, that left phosphorus at +5. Water is going to show up a lot in redox equations, so we should just get very familiar with its oxidation numbers. In a covalent compound, oxygen is -2 and hydrogen is +1. That's sort of your easy dead giveaway in these types of problems. Phosphoric acid we did earlier, so let's review it again. We did the oxidation numbers for this earlier. So it's a covalent compound, which makes oxygen -2 and hydrogen +1. So we have 4 -2s, 3 +1s. That's a total of -5. We saw that phosphorus had to be +5 for that to work. And then for HCl, just two things bonded to each other, covalent compound, hydrogen +1, chlorine -1. They almost always follow those rules. So those are the oxidation numbers. And if we look at each element on the reactants and product side, what we find is that phosphorus is +5 on the reactant side and still +5 on the product side. For oxygen, it appears twice on the reactant side, but it's -2 in both cases. -2 in POCl3, -2 in water. So on the reactant side, it's always -2, and then on the product side, it's also only -2. If we go to chlorine, chlorine is -1 on the reactant side in POCl3, and it's also -1 on the product side in HCl. And then finally, hydrogen starts out as +1 in water, and then appears twice on the product side, but it's both +1. +1 for phosphoric acid, +1 for HCl. So hydrogen always +1. So in looking at the oxidation numbers for this one here, we see that none of them are changing. And because we don't have any changing oxidation numbers, this one is not a redox reaction. This one ends up being, it's not obvious from what it looks like. It's not the type of acid-base reaction that we know about, but this is just an acid-base reaction. So in some cases, you'll easily be able to identify it as an acid-base or precipitation reaction. In this case, it wasn't obvious from looking at the reactants and products. It doesn't follow the usual acid plus base makes water and ionic compound, so it's not that type of acid-base reaction, but it is a acid-base reaction, but you can tell just by looking at oxidation numbers that it's not a redox equation, which is what we were asking here. All right, so you have to, again, look at changes in oxidation numbers to help you decide if it's going to be a redox equation or not. Now, the most important thing you're going to have to do in this part of the course with redox reactions is learn how to balance them. I mean, assigning oxidation numbers, assigning oxidizing and reducing agents, that's going to come up, but you will see multiple test questions in the future. I'll just warn you about it now, both on the second exam and on the final exam. You'll see multiple test questions that involve balancing redox equations. So it's something we have to learn how to do effectively. So we're going to go through a step-by-step approach for how to do this. So here's the redox equation we're going to balance. It's an ionic equation. It has Cl minus, MnO4 minus, and H plus as reactants. And on the product side, it has hypochlorite, ClO minus, manganese 3 plus, and water. So let's go through the series of steps we're going to have to do to be able to balance any redox equation. So the first thing we have to do is we have to assign the oxidation number of each element or each atom in the equation. So we're going to assign every oxidation number first. And so that's what we're going to do here. So here we have Cl minus, ion by itself, so the oxidation number is just the charge. That one's easy. MnO4 minus is a tough one to do, but we're going to see it in a lot of these redox equations. So oxygen in compounds is going to be -2 with rare exceptions. So we have 4 -2s from oxygen. The overall oxidation numbers have to add up to be -1, so manganese has to be +7. So 4 -2s is -8. +7 adds up to -1, which is the overall charge of the permanganate ion. H plus ion by itself, so it's just the charge +1. ClO minus, another one that's not terribly straightforward, but we have oxygen in a covalent compound makes it -2. So we have a -2. The overall sum has to be -1 because that's also the charge of that ion, so chlorine has to be +1 in this case for those to add up correctly. So +1 from chlorine, -2 from oxygen adds up to -1. Manganese +3 is an ion by itself, so it's just going to be the charge. And then what we have for water is our old friend, which is -2 for oxygen, +1 for hydrogen. Okay, so those are all the oxidation numbers. That's the first thing we have to do. There's not really a shortcut around that. From there, what we have to do is we have to determine the number of electrons that are lost and gained for everything that changes the oxidation number. So we're going to determine the number of electrons lost or gained for each atom that changes its oxidation number. Now, how do we do that? That's going to be based on the difference in their oxidation number from the reactants in the product side. So if we go back up and see which ones are changing, we'll notice that chlorine is -1 on the reactant side and +1 on the product side. So that's one of the ones that's changing its oxidation number. And so this one here, Cl minus to ClO minus, -1 to +1 is a difference of 2. The difference between -1 and +1 is 2 on a number line. So this one's going to be 2 electrons. Now, technically speaking, we can identify that this is losing 2 electrons. It doesn't really matter so much if we accurately determine whether it's losing or gaining electrons, because what's going to be important later on is just making sure they're the same number. But this one is losing electrons because the oxidation number is getting bigger. It's getting oxidized. The other one that was changing was manganese. Manganese was +7 here on this reactant in MnO4 minus and +3 on the product side. So that's the other one that's changing. So when we connect those two, it's a difference of 4. 7 minus 3 is 4. The oxidation number is getting smaller, so it's gaining 4 electrons. Again, whether you get it correct, which one is losing and gaining electrons, for this type of problem, if you're just balancing the equation, it's not important. You just need to know the number of electrons. 2 electrons for -1 to +1, 4 electrons for +7 to +3. So then once we identify that, the next thing we're going to do is we're going to add coefficients to balance the electrons that are lost and gained. So the first thing we're going to make sure is that the number of electrons that are lost and the number of electrons that are gained are the same. Again, we can't create or destroy electrons in a redox equation. Whatever is lost from one substance has to be gained by the other, so we need to have the same number of electrons involved for both of those. So as we saw, Cl minus to ClO minus was a difference of 2 electrons being lost. And then what we had for permanganate to Mn3 plus, Let me do that in red again to keep it consistent with the last one. This one here was a difference of gaining 4 electrons. So those two numbers need to be the same, and right now they're not, because we have 2 electrons for Cl minus going to ClO minus, but it's 4 electrons for the manganese part, so those need to be the same. The way that we make them the same is we have to find the, I guess, the least common multiple or between them, which is going to be 2. So we have to double this to make sure that now they're both 4. So if we have this one happening twice, that's going to mean we were losing 4 electrons and gaining 4 electrons. And so we're going to have to put coefficients of 2 in front of each of those so that that process happens twice for a total of 4 electrons. And then we're going to set the coefficient as 1 for these two because we don't want to change those at all because that's going to change the number of electrons that are involved. So this is happening 1 time for a total of 4 electrons. This process is happening 2 times to give us also a total of 4 electrons. So once we have those coefficients set, which again is going to be a 2, a 1, a 2, and a 1 to make sure the number of electrons are balanced, we balance the rest by inspection. And that means just making sure that the number of atoms are the same on both sides. So we don't want to touch these first 4 coefficients that we've set because that's going to throw off the number of electrons that we have. But all we have left is H plus and water. So usually the way we're going to do this is we're going to balance water first to make sure that we have the same number of oxygen atoms on both sides. So on the left side of the equation we have 4 oxygen atoms from MnO4 minus. On the right side we have 2 from ClO minus, so we need 2 more from water to make sure we have 4 oxygen atoms on each side. And now by putting in 2 water molecules, that gives us 4 hydrogens on the right side. So we also need 4 H pluses on the left to balance those. So we're going to do those by inspection, and usually it often is going to involve water and H plus or something like that is the last things you balance to make sure you have the same number of atoms on each side. So this one is now totally balanced. The number of electrons are correctly balanced, and the rest of the coefficients are there to make sure that the mass balance is also preserved in this. All right, so now we're going to just close with a few examples of using this approach for doing the oxidation numbers. All right, so here we have this reaction here. Dichromate plus I minus plus H plus going to chromium 3 plus iodine and water. So again, an element is involved, I2, so that identifies this easily as a redox reaction if we weren't sure about that. But to balance it, we have to assign all the oxidation numbers. So dichromate is another tough one. It doesn't get much tougher than this. So we have 7 oxygens, but those are -2 each whenever oxygen is in a compound. So 7 minus 2s is -14. The total needs to be -2. So that means each chromium has to be +6. So let's make sure we follow that. 2 plus 6s from chromium is +12. 7 minus 2s from oxygen is -14. 12 minus 14 is -2, which is the overall charge. So again, there's 2 chromiums in the formula, so each of them is +6. The total is +12, but each one is +6. For I minus, that's an ion by itself, so the charge is just the oxidation number. Same with H plus. Same with chromium 3 plus, ion by itself, so the charge is the oxidation number. I2 is an element, so it's going to be 0. And then water is our old friend, +1 and -2. All right, so those are all the oxidation numbers. And then we have to go and figure out which ones are changing and how many electrons there are. Now, one slight complication of this one is we notice that on the reactant side we have, so one of the ones that's changing here is chromium. It's going from +6 to +3. But on the reactant side we have 2 chromiums that are +6. On the product side we only have 1 chromium that's +3. So it's easy to make mistakes with counting electrons when this happens. So the way that I like to do this to help myself is recognize, like, okay, so we have 2 chromiums over here on the left side. Whatever the coefficient is over here has to be 2 times that to make sure that we have the same number of chromiums on each side. So now when we're counting electrons, what we have is we have 2 plus 6s, which are, so 2 chromium plus 6. On the left, going to 2 chromium plus 3s on the right. And so each chromium is changing by 3 electrons. a difference of +6 to +3, but it's happening twice because there's 2 chromiums that are +6 going to 2 chromiums that are +3. So in total, it's a 6 electron process. Again, it's sort of easy to miscount that if we're not careful. It's going to get in my way, so let me move that. But basically, again, the argument is that each chromium is going from +6 to +3, so it's 3 electrons, but it's happening twice because there's 2 chromium +6s going to 2 chromium +3s, so a total of 6 electrons. And then we have a similar story with iodine, because just like chromium, we have I-, just one iodine by itself, but it's converting to I2, which has 2 iodines. So these are the ones that are also changing, -1 to 0. But again, to help ourselves with counting electrons, we have 2 I- there to form 1 I2. There has to be, whatever the coefficient of iodine is, has to be double that of I2 to make sure we have the same number of iodine atoms on both sides. So when we're counting those, we have 2 I- on the left going to I2 on the right. Each I- is changing its oxidation number by 1. It's going from -1 to 0, but there's 2 of them, so it's a total of 2 electrons. 1 electron for each iodine, and then 2. So it's going to be 1 electron change for each iodine, but it's happening twice, so it's a total of 2 electrons. All right, so that's going to be how we count electrons. It's a little bit more challenging in this case because the ones that are changing oxidation numbers, they appear more than one side on different sides of the equation. All right, but we have to make sure now that these in total are all balanced. So right now we have 6 electrons for chromium and only 2 electrons for iodine. So what we need to do is we need to make those the same by tripling that to also make it a total of 6. So what that does, I'll write it down here now and not undo what I've already written. What we're going to do now is we have to triple the coefficients that are involved in this I- I2 part of the reaction. So we keep the coefficient of 1 on Cr2O72-, but now we have to triple the coefficients for iodine. So instead of a 2, that becomes a 6. We have to balance H+ last, so we still need a coefficient for that. And then the product side, we have 2 chromium +3s. We don't change the coefficient for that. I2, we had to triple its coefficient, so it becomes a 3. And then we have water as the last one. They'll still need a balance. So now we've set the coefficients for this one, this one, this one, this one, the ones that were changing their oxidation number. And just like the last one, all that's left is to balance H+ and water. All right, so for water, we do that. We have to make sure there's the same number of oxygen atoms on each side. We have 7 oxygen atoms in dichromate, so we need 7 waters to balance that. By adding 7 waters, that's 14 hydrogens, so this is going to get a 14 to balance that as well. So this would be the final balanced form of this equation. So counting electrons was a little bit more tricky here because we had 2 atoms changing their oxidation number in each case. But once we get the number of electrons correct, we just have to make sure that the number of electrons is equal between the 2 and then balance the other coefficients by inspection. All right, we're going to do just 2 more to finish off today. Make sure that's right. So we have another one here that involves potassium periodate with NH3 ammonia forming KiN2 and H2O. All right, so we have an element involved, so it's definitely a redox equation. So let's assign all the oxidation numbers to help us balance. So KiO4, this is a ionic compound, potassium with a polyatomic periodate. So the metal is going to be +1 because potassium is always +1. Remember, it's in the first column here. Oxygen is -2 whenever it's involved in compounds, or very rarely it's anything but that. And so if we have a +1 and 4 -2s, that's -7. Iodine needs to be +7. Iodine's in group 7, so that's the highest oxidation number it can have. NH3 is fairly straightforward. Hydrogen is +1 when it's bonded to nonmetals. 3 +1s is a +3. Nitrogen has to be -3. For Ki, it's an ionic compound. +1 still for potassium. And again, iodine, group 7, is going to be a -1 anion. So ionic compounds, we just assign the charges as the oxidation numbers. And then nitrogen, element by itself, has to be 0 oxidation number, and then our old friend water, +1 and -2. All right, so those are oxidation numbers. Now we just have to find the ones that are changing. So iodine is going from +7 to +1. Sorry, +7 to -1 for iodine. +7 to -1. So the difference between that, 7 to -1, is 8 electrons for that part. The other one that's changing is nitrogen. It's going from -3 to 0, but again, this is a situation where we have 2 of those on the product side. So we're going to put a coefficient of 2 here to remind ourselves that it's happening twice. Each nitrogen atom is going from -3 to 0 to form N2. So it's a total of 6 electrons. 2 -3s to 0. 3 electrons each for a total of 6. But now we still need to adjust coefficients to make sure that these balance each other up. So we have 8 electrons for iodine going from +7 to -1, 6 electrons for 2 nitrogens going from -3 to 0. So the way that we can balance those, we have to find the least common multiple of those. So the least common multiple of 8 and 6 is 24. So we triple that to make it 24 electrons. And we quadruple that to make it also 24 electrons. So what that leads to then are the following coefficients. We had to triple the coefficients on KiO4 and Ki, so we get a coefficient of 3 in front of each of those. And then for nitrogen, what we had was we have to quadruple the coefficients. It was originally 6 electrons, need to happen 4 times to get the total of 24. So this quadruples to 8, and nitrogen quadruples to 4. And then finally, we have to get oxygen balanced by adding the correct number of waters to this product side. So on the left side, we have 3 times 4 is 12 oxygens. And so we need to have 12 waters to balance that. Now we can also check that hydrogen is balanced, because we didn't have to do that one separately. We have 12 times 2 is 24, 8 times 3 is 24. So the same number of hydrogen and oxygen on both sides once we put a coefficient of 12 in front of water. So this question here asks us to determine the sum of the coefficients. That's one common way that we might ask it in Blackboard. So the sum in this case, not that that's a useful number, but what we would report to answer this question is 3 plus 8 is 11, plus 3 is 14, plus 4 is 18, plus 12 is 30. So the sum of all the coefficients equals 30. So we get some pretty big coefficients. This one would not be very easy to balance by inspection, but if you follow the oxidation number approach, we're able to get those coefficients pretty easily. All right, and then finally, the last one that we'll go through is an example, but you're going to see a lot of these on your homework assignments, so make sure you practice a lot on your own as well, is this one here, where we have to determine the coefficient for nitric acid. Now, this one is a little bit tricky, as we'll see, for a reason that we haven't seen yet, but the oxidation number part of it is not too bad. So what we have is zinc by itself, that's an element, so its oxidation number is 0. HNO3, I think we did this one earlier, but anyway, oxygen is -2 when it makes covalent compounds, hydrogen is +1, so we have 3 -2s is -6, +1 is -5, that means we need +5 on nitrogen for those to all add up to 0. For zinc nitrate, this one is a little bit tricky to do, but it's an ionic compound, metal with an anion. So it's 2 nitrates, which is -1, so that means the charge on the metal has to be +2. And then for NO3-, if we could assign the oxidation numbers for that on its own. So NO3- is the anion. And if we follow the rules for oxidation numbers, we'll get there. But one thing that's helpful to recognize is that if you have an acid and it's just losing its H+ to make the anion, which is what's happening. So this is going from nitric acid, HNO3, to just the nitrate ion paired with zinc. You don't change the oxidation numbers when you do that. So NO3- is still +5 for nitrogen and -2 for oxygen. Again, we can confirm that oxygen is always -2 in compounds, and nitrogen has to be +5 for the total add up to the charge. But it's helpful to just remember that when you're just adding or removing H+ from an acid, you don't change the oxidation numbers when you do that. For NO, nitrogen and oxygen, -2 for oxygen when it's in a covalent compound, which means that nitrogen has to be +2 in that case. And then for water, you have +1 and -2 always. Okay, so then the ones that are changing oxidation numbers, we have zinc going from 0 to +2, that's 2 electrons. And we also have nitrogen going from +5 to +2, that's a difference of 3, so that'd be a 3-electron process. Now, one thing though that's a little bit tricky about this one is that we notice that nitrogen is going from +5 to +2 when you go from HNO3 to NO, but we also have some nitrogen that's not changing. We have HNO3 is +5, and it's still +5 here. So we also have some nitrogen that's not changing its oxidation number. So how do we deal with that? So we need to balance the number of electrons, but we also need to make sure that the number of nitrogen atoms is the same on both sides. So how do we deal with that? Where if we use the oxidation number approach, we're not necessarily going to get the correct number of nitrogen atoms on both sides. So the way that I like to handle this, there's no perfect solution, and whatever you choose to do is fine with me. But what I like to do is actually separate the HNO3 into two pieces when we balance. So we have zinc, HNO3. We're actually going to write HNO3 twice and balance the two pieces separately before combining them at the end. And I'll show you why we do that here in a second. So what we're doing here is recognizing that, again, this is changing from 0 to +2. That's 2 electrons. We have this one going from +5 to +2. That's 3 electrons. Then we also have some nitrogen that's not changing. So we're going to leave this part of it here to balance at the end by inspection. So we're going to put a coefficient in front of HNO3 to make sure that the number of electrons that are transferred are the same. And then at the end by inspection, we're going to add more HNO3 to make sure that all the atoms are balanced. All right, so when we do this, what we see is that the zinc to zinc 2+, again, that's going from 0 to +2. That's a 2 electron change, and this is going from +5 to +2, which is a 3 electron change. So to make those two equal to each other, the least common multiple of 2 and 3 is 6. So we're going to triple that, and we're going to double that. And so what that leads to then are the following coefficients, where we have a 3 in front of zinc. That has to be doubled, so we're going to get a 2 in front of the first HNO3. We're going to add more HNO3 in a little bit just to balance everything out at the end. And then we're going to have, again, a 3 in front of zinc nitrate, because we need 3 of those. A 2 in front of NO to, again, keep the balanced electrons, and then we'll have to do water at the end as well. All right, so this is what we have so far, and these are the coefficients that we want to basically leave as is, because those are used to balance the number of electrons transferred. But now we can add more HNO3 and more water to make sure that everything is totally balanced. So what we find is that in these 3 zinc nitrates that we have here, that's going to be 6 additional nitrogen atoms, or 6 additional nitrate ions in total. 3 times 2 is 6, so we need to add 6 more HNO3s to account for that. So by adding 6 more of those, we now have total balance of nitrogen. And then to make sure oxygen is balanced, here on the left side we have 6 plus 18 is 24 oxygen atoms on the left. On the right we have 18 plus 2 is 20, so we need 4 more. So we're going to need to have 4 waters to make sure that there's 24 oxygen atoms on each side. So we do those two by inspection. Now finally we can simplify this and combine the 2 pieces of HNO3 that we balanced separately to get 3 zincs, 8 total HNO3. 2 of them are being reduced and involved in electron transfer. 6 of them are just providing counter ions for the zinc. And then on the product side we don't have to change anything. It's just 3 zinc nitrates, 2 NOs, and 4 waters. All right, so that one was another little wrinkle that we haven't seen yet, where sometimes you'll have atoms that are, both involved in the redox process, like nitrogen was, but also involved in processes that are not redox in nature, and so you had to balance those separately. And there's, you could do it different ways. You don't necessarily have to break it up like I did, but I think that's just helpful because it allows us to make sure the number of electrons are balanced first, and then in a separate step we can add the correct number of additional ones that we need to keep all the mass balanced, all the atoms balanced. All right, so that takes us to the end of this. So that was the last category of aqueous reactions. So you're going to have your spring break now, which I hope you all have a good time with that. And then when we get back, we're going to finish Chapter 6 with solution stoichiometry as we get ready for the last homework assignment that's going to lead into our second exam. All right, so again, I'll see you guys in a while, but if you have any questions about what we learned in either of these lectures or anything else that's going on in the course, please don't hesitate to contact me. I will be out of town, but I'll be able to be in regular contact, so reach out if you need anything. All right, see you in a couple weeks, I guess.